Well, welcome back to our course, Computer Organization and Architecture. We're now going to go into our next major section. And so for this chapter, we're talking about process structure and function. But just to give a perspective, we're going to be talking about for the next 4 lectures, the central processing unit. And we'll get a lot of insight into that. This is a key component that we need to get a good understanding about how it works. So here's the material that we'll cover in this lecture. First, we'll talk about the processor organization. We'll talk about the register organization. And you'll recall that we have been talking about some of these in previous lectures. And so hopefully now, when we're focusing on the CPU, the central processing unit in particular, it'll have a little bit more clarity and help you to build a better understanding of how all this works. We'll talk about the instruction cycle, the fetch execute, and then more details about that. We'll be talking about the different types of processors. We'll talk about the x86 processor family, the register organization and interrupt process. We'll talk about instruction pipelining. And so this is how you're trying to create a lean, mean ability to do a lot of commands, a lot of operations, one right after another, or depending on how the CPU is set up, maybe having multiple cores that you divvy some of that up. And then finally, we'll talk about the ARM processor, the processor organization, processor modes, register organization, and interrupt processing. So to understand the organization of the processor, let us consider the requirements placed on the processor. So that's what we're listing here. The things that it must do. The fetch instruction, the processor reads an instruction from memory, the register, cache, and main memory. The interrupt instruction, the instruction is decoded to determine what action is required. Fetch data, the execution of the instruction may require reading data from memory or an I/O module. Process data, the execution of an instruction may require performing some arithmetic or logical operations on data. Write data, the results of an execution may require writing data to memory or an I/O module. To do these things, it should be clear that the processor needs to store some data temporarily. It must remember the location of the last instruction so that it can know where to get the next instruction. It needs to store instructions and data temporarily while an instruction is being executed. In other words, a processor needs a small internal memory. And so we have talked a little bit about that, and now we'll get into some of those details in a little bit more fidelity. Figure 16.1 is a simplified view of the internal structure of a processor. The reader will recall the major components of the processor are the arithmetic logic unit, the control unit. And so as you are reviewing this lecture, we want you to be mindful of those things. So the ALU does the actual computation or processing of the data. The control unit controls the movement of the data and instructions into and out of the processor, and it controls the operation of the ALU. In addition, the figure shows a minimal internal memory consisting of a set of storage locations called registers. And so this is one of the key places where a CPU has access to memory, the fastest memory. The data transfer and logic control paths are indicated, including an element labeled internal processor bus. This element is needed to transfer data between the various registers and the ALU, because the ALU in fact operates only on data in the internal processor memory. The figure also shows typical basic elements of the ALU. Note the similarity between the internal structure of the computer as a whole and the internal structure of the processor. It's like a mini computational environment in the CPU. In both cases, there is a small collection of major elements: computer, processor, I/O, memory, processor, control unit, ALU, and registers. connected by a data path. And so we have the elements of a von Neumann architecture, if you recall what that is, the CPU, the memory, and the input and output. All of those elements are found in the CPU. And as you may recall back in chapter 4, we discussed a computer system employs a memory hierarchy. At memory levels of the hierarchy, memory is faster, smaller, and more expensive per bit. With a processor, there is a set of registers that function as a level of memory above main memory and cache in the hierarchy. The registers in the processor perform two roles. There's user visible registers, which enable the machine or assembly language programmer to minimize main memory references by optimizing use of registers. Then there's control and status registers. It's used by the control unit to control the operations of the processor and by privilege, operating system programs to control the execution of the programs. There's not a clean separation of registers for these two categories. For example, on some machines, the program counter is usually visible, for example, for x86 architectures, but on many it is not. For the purpose of the following discussion, however, we will use these categories that were defined here: user visible registers and control and status registers. A user visible register is one that may be referenced by means of a machine language that the processor executes. We can characterize these in the following categories: general purpose, data, address, and control codes. General purpose registers can be assigned to a variety of functions by the programmer. Sometimes their use within the instruction set is orthogonal to the operation. That is, any general purpose register can contain the operand for any opcode. This provides true general purpose register use. Often, however, there are restrictions. For example, there may be dedicated registers for floating point and stack operations. In some cases, general purpose registers can be used for addressing functions, for example, register indirect displacement. In other cases, there is a partial or clean separation between the registers and address registers. The data registers may be used only to hold data and cannot be employed in the calculation of the operand address. The address registers may themselves be somewhat general purpose, or they may be devoted to a particular addressing mode. Examples include the following. So you can have segment pointers. If a machine with a segment addressing, you can go back to section 9.3 to review that. A segment register holds the address of the base of the segment. There may be multiple registers, for example, one for the operating system and one for the current process. Index registers, these are used for index addressing and may be auto-indexed. Stack pointer, if there is a user visible stack addressing, then typically there is a dedicated register that points to the top of the stack. This allows implicit addressing, that is push, pop, and other stack instructions need not contain an explicit stack operand. There are several design issues to be addressed here. An important issue is whether to use completely general purpose registers or to specialize their use. We have already touched on this issue in the preceding chapter because it affects instruction set design. With the use of specialized registers, it can generally be implicit in the opcode which type of register a certain operand specifier refers to. The operand specifier must only identify one of a set of specialized registers rather than one out of the registers, thus saving bits. On the other hand, this specialization limits the programmer's flexibility. Another design issue is the number of registers, either general purpose or data plus address, to be provided. Again, this affects instruction set design because more registers require more operand specifier bits. As we previously discussed, somewhere between 8 and 32 registers appear optimum. And so studies have demonstrated that is a true fact. Few registers result in more memory references. More registers do not noticeably reduce memory references. However, a new approach which finds advantage in the use of hundreds of registers is exhibited in some RISC systems and are discussed in chapter 17. ARM is an example of a RISC system, so keep that in mind if you don't recall that off the top of your head. Finally, there is an issue of register length. Registers that must hold addresses obviously must be at least long enough to hold the largest address. Data registers should be able to hold value of most data types. Some machines allow two contiguous registers to be used as one for holding double length values. A final category of registers, which is at least partially visible to the user, holds condition codes, also referred to as flags. Condition codes are bits set by the processor hardware as a result of operations. For example, an arithmetic operation may produce a positive, negative, zero, or overflow result. In addition to the result itself being stored in a register or memory, a condition code is also set. The code may subsequently be tested as part of a conditional branch operation. Condition codes are collected into one or more registers. Usually they form part of a control register. Generally, machine instructions allow these bits to be read by implicit reference, but the programmer cannot alter them. So many processors, including those based on the IA64 architecture and the MIPS processor, so the two major categories we've been focusing on for the most part in this class, do not use condition codes at all. Rather, conditional branch instructions specify a comparison to be made and act on the result of the comparison without storing a condition code. Table 16.1, which we're showing here, list key advantages and disadvantages of control codes. In some machines, a subroutine call will result in the automatic saving of all user visible registers to be restored on return. The processor performs a saving and restoring as part of the execution of call and return instructions. This allows each subroutine to use the user visible registers independently. On other machines, it is a responsibility of the programmer to save the contents of the relevant user visible registers prior to the subroutine call by including instructions for this purpose in the program. There are a variety of processor registers that are employed to control the operation of the processor. Most of them on most machines are not visible to the user. Some of them may be visible to machine instructions executed in a control or operating system mode. Of course, different machines will have different register organizations and use different terminology. We list here a recently complete list of register types with a brief description. So 4 registers are essential to instruction execution. First, the program counter. It contains the address of the instruction to be fetched. Instruction register, or IR, contains the instruction most recently fetched. Memory address register, or MAR, contains the address of a location in the memory. Memory buffer register, or MBR, contains a word of data to be written to memory or the word most recently read. Not all processors have internal registers designated as MAR and MBR, but some equivalent buffering mechanism is needed, whereby the bits to be transferred to the system must be staged and the bits to be read from the data bus are temporarily stored. Typically, the processor updates the PC, the program counter, after each instruction fetch, so the PC always points to the next instruction to be executed. A branch or skip instruction will also modify the contents of the PC. The fetched instruction is loaded into the IR, where the opcode and the operand specifiers are analyzed. Data are exchanged with memory using the MAR and MBR. In a bus organized system, the MAR connects directly to the address bus, and the MBR connects directly to the data bus. User visible registers in turn exchange data with the MBR. The four registers just mentioned are used for the movement of data between the processor and memory. Within the processor, data must be presented to the ALU for processing. The ALU may have direct access to the MBR and user visible registers. Alternatively, there may be additional buffering registers at the boundary to the ALU. These registers serve as input and output registers for the ALU and exchange data with the MBR and user visible registers. Many processor designs include a register or set of registers, often known as the program status word or PSW, that contains status information. The PSW typically contains condition codes plus other status information. Common fields or flags include the following: sign contains the sign of the result of the last arithmetic operation. 0, when set the result is 0. It's set when the result is 0. Carry is set when the operation results in a carry, that is addition into a borrow. The carry, it is set if the operation result is a carry, which would be the case for addition, or borrow, which would be the case for subtraction, out of a higher order bit. It's used for multi-word arithmetic operations. Equals, it is set if any logical comparison results in equality. Overflow, which is used to indicate arithmetic overflow. Interrupt enable / disable, it's used to enable or disable interrupts. And finally, supervisor, it indicates whether the processor is executing in supervisor or user mode. Certain privileged instructions can be executed only in supervisor mode, and certain areas of memory can be accessed only in supervisor mode. A number of other registers related to status and control might be found in a particular processor design. There may be a pointer to a block of memory containing additional status information, for example, process control blocks. In machines using vectored interrupts, an interrupt vector register may be provided. If a stack is used to implement certain functions, for example, subroutine calls, then a system stack pointer is needed. Final table pointer is used with a virtual memory system. Registers may be used to coordinate the control of I/O operations. A number of factors go into the design of control and status register organization. One key issue is operating system support. Certain types of control information are of specific utility to the operating system. If the processor designer has a functional understanding of the operating system to be used, then the register organization can to some extent be tailored to the operating system. Another key design decision is the allocation of control information between register and memory. It is common to dedicate the first, that is the lower few hundred or thousand words of memory for control purposes. The designer must decide how much control information should be in register and how much in memory. The usual trade-off of cost versus speed arises to try and determine that mix. Here we're showing an example of microprocessor register organizations. It is instructive to examine and compare the register organization of comparable systems. In this section, we will look at two 16-bit processors that were designed at about the same time: the Motorola 68000 and the Intel 8086. So an early version of each one of these things to have it relatively simple. Figure 16.2a and b depict the register organization of each. Purely internal registers, such as memory address registers, are not shown. The Motorola 68000 partitions its 32-bit registers into 8 data registers and 9 address registers. The 8 data registers are used primarily for data manipulation and are also used in addressing as index registers. The width of the registers allow 8, 16, and 32-bit data operations determined by opcode. The address registers contain 32 bits, that is no segmentation addresses. Two of these registers are also used as stack pointers, one for users and one for the operating system, depending on the current execution mode. Both registers are numbered 7 because only one can be used at a time. The Motorola 68000 also includes a 32-bit program counter and a 16-bit status register. The Motorola team wanted a very regular instruction set with no special purpose registers. Concern for code efficiency led them to divide the registers into 2 functional components, saving 1 bit on each register specifier. This seems a reasonable compromise between complete generality and code compaction. On the other hand, the Intel 8086 takes a different approach to register organization. Every register is a special purpose, although some registers are also usable as general purpose. The 8086 contains 4 16-bit data registers that are addressable on a byte or 16-bit basis and 4-bit pointer and index registers. The data registers can be used as general purpose in some instructions. In others, the registers are used implicitly. For example, a multiply instruction always uses the accumulator. The 4-pointer registers are also used implicitly in a number of operations, each contain a segment offset. There are also 4 16-bit segment registers. 3 of the 4 segment registers are used in a dedicated implicit fashion to point to the segment of the current instruction, which is useful for branch instructions. A segment containing data and a segment containing a stack respectively. These dedicated and implicit uses provide for compact encoding at the cost of reducing flexibility. The 8086 also includes an instruction pointer and a set of 1-bit status and control flags. The point of this comparison should be clear. There's no universally accepted philosophy concerning the best way to organize processor registers. As with overall instruction set design and so many other processor design issues, it is still a matter of judgment and taste. A second instructive point concerning register organization is illustrated in 16.3c, and we'll get to that shortly. This figure shows the user visible registers organization for the Intel 8386. Which is a 32-bit microprocessor designated as an extension of the 8086. The 8386 uses 32-bit registers. However, to provide upward compatibility for programs written on the earlier machines, the 8386 retains the original registers organization embedded in the new organization. Given this design constraint, the architecture of the 32-bit processors had limited flexibility in designing the register organization. So if you're doing backward compatibility, that's always going to be a constraint, and we're seeing a little bit of evidence of how that shows up as we think about these and then look towards future versions of what's taking place. So we have the 8086, and here we're seeing things that are similar to what we saw over here for the general registers for the initial 86, but then we have these E, so whatever acronym you want to be thinking about, enhanced, to help you be thinking of the difference. Those are things that are showing up there. So in section 3.2, you might recall we described the processor's instruction cycle. That was in figure 3.9. To recall, an instruction cycle includes the following stages. We have the fetch execute cycle. That's main parts of this, but there's more details. Fetch is read the next instruction from the memory into the processor. Execute, it interrupts the opcode and performs the indicated operation. Interrupt, if interrupts are enabled and an interrupt has occurred, you save the current processor state and service the interrupt. Then you go back and what you were doing before the interrupt. We are now in a position to elaborate somewhat on the instruction cycle. First, we must introduce an additional stage known as the indirect cycle. So we're getting into more details. We have seen in chapter 14 that the execution of an instruction may involve one or more operands in memory, each of which requires memory access. Further, if indirect addressing is used, then the additional memory accesses are required. We can think of fetching of indirect addresses as one or more instruction stages. The result is shown in figure 16.3, what we're listing here. The main line of activity consists of alternating instruction fetches and instruction execution activities. After instruction is fetched, it is examined to determine if any indirect addressing is involved. If so, the required operands are fetched using indirect addressing. Following execution, an interrupt may be processed before the next instruction. So thus we're seeing a more detailed thing of what's going on with interrupt and indirect possibilities. Another way to view this process is shown in figure 16.4, which is a revised version of what we were showing in figure 3.12 in chapter 3. This illustrates more correctly the nature of the instruction cycle. Once an instruction is fetched, its operand specifiers must be identified. Each input operand in memory is then fetched, and this process may require indirect addressing. Register-based operands need not be fetched. Once the opcode is executed, a similar process may be needed to store the result in main memory. So you can go ahead and pause the video and spend a little bit more time looking over that chart if you'd like. The exact sequence of events during an instruction cycle depends on the design of the processor. We can, however, indicate in general terms what must happen. Let's assume that a processor that employs a memory address register MAR, a memory buffer register MBR, program counter PC, and an instruction register IR. During the fetch cycle, an instruction is read from memory. Figure 16.5 that we're showing here shows the cycle, the flow of data during the cycle. The PC contains the address of the next instruction to be fetched. The address is moved to the MAR and placed on the address bus. The control unit requests a memory read, and the result is placed on the data bus and copied into the MBR and then moved on to the IR. Meanwhile, the program counter PC is incremented by 1, preparing for the next fetch. Once the fetch cycle is over, the control unit examines the contents of the IR to determine if it contains an operand specifier using indirect addressing. If so, an indirect cycle is performed, as shown in figure 16.6 that we're showing now. This is a simple cycle. The rightmost n bits of the MBR, which contain the address reference, are transferred to the MAR. Then the control unit requests a memory read to get the desired address of the operand into the MBR. The fetch and the indirect cycles are simple and predictable. The execute cycle takes many forms. The form depends on which of the various machine instructions is in the IR. This cycle may involve transferring data among registers, read or write from the memory or IO, and or the invocation of the ALU. Like the fetch and indirect cycle, the interrupt cycle is simple and predictable. We're showing this in this figure that we're listing now, figure 16.7. The current contents of the PC must be saved so that the processor can resume normal activity after the interrupt. Thus, the contents of the PC are transferred to the MBR to be written into memory. The special memory location reserved for this purpose is loaded into the MAR from the control unit. It might, for example, be a stack pointer. The PC is loaded with the address of the interrupt routine. As a result, the next instruction cycle will begin by fetching the appropriate instruction. As computer systems evolve, greater performance can be achieved by taking advantage of improvements in technology such as faster circuitry. In addition, organizational enhancements to the processor can improve performance. We have already seen some examples of this, such as the use of multiple registers rather than a single accumulator, and the use of cache memory. Another organizational approach, which is quite common, is instruction pipelining. Instruction pipelining is similar to the use of assembly line in a manufacturing plant. An assembly line takes advantage of the fact that a product goes through various stages of production. By laying the production process out in an assembly line, products at various stages can be worked on simultaneously. This process is also referred to pipelining because, as in a pipeline, new inputs are accepted at one end before previously accepted inputs appear as outputs at the other end. To apply this concept to instruction execution, we must recognize that, in fact, an instruction has a number of stages. Figure 16.4, for example, breaks the instruction cycle into 10 tasks which occur in sequence. Clearly, there should be some opportunity for pipelining. As a simple approach, consider subdividing instruction processing into two stages: fetch instruction and execute instruction. There are times during the execution of an instruction when the main memory is not being accessed. This time could be used to fetch the next instruction in parallel with the execution of the current one. Figure 16.8a on the top that we're showing in this figure depicts this approach. The pipeline has two dependent stages. The first stage fetches an instruction and buffers it. When the second stage is free, the first stage passes the buffered instruction. While the second stage is executing the instruction, the first stage takes advantage of an unused memory cycle to fetch and buffer the next instruction. This is called the instruction prefetch or fetch overlap. Note that this approach, which involves instruction buffering, requires more registers. In general, pipelining requires faster registers called latches that store intermediate value stages. Figure 16.9 that we're showing here illustrates this in a simplified form for a three-stage pipeline. The latches serve to decouple the stages from each other. Information flows between adjacent stages under the control of a common clock applied to the latches simultaneously. As each clock cycle ends, the latches gate in their input and forward them into the next stage, where the required operation is performed. This simplified picture omits several details. Each stage may consist of multiple execution units that cooperate in performing the required operation. In addition, the latches may be extended with multipliers that allow the input to a latch to come from a subsequent stage, which is feedback, or from a stage prior to the just preceding stage, which is feed forward. Should be clear that this process will speed up instruction execution. If the fetch and execution stages were of equal duration, the instruction cycle time would be halved. However, if we look more closely at this pipeline in figure 16.8b, so you can look back at that, we will see that this doubling of execution rate is unlikely for two reasons. First, the execution time will generally be longer than the fetch time. Execution will involve reading and storing operands and the performance of some operations. Thus, the fetch stage may have to wait for some time before it can empty its buffer. Two, a conditional branch instruction makes the address of the next instruction to be fetched unknown. Thus, the fetch stage must wait until it receives the next instruction address from the execute stage. The execute stage may then have to wait until the next instruction is fetched. Guessing can reduce the time lost from the second reason. A simple rule is to follow this. When a conditional branch instruction is passed on from the fetch to the execute stage, the fetch stage fetches the next instruction in memory after the branch instruction. Then if the branch is not taken, no time is lost. If the branch is taken, the fetch instruction must be discarded and a new instruction fetched. So we're seeing strategies of how to try and make things work more efficiently, a common theme that we covered in other parts of the computational environment we've looked at. With these factors reduce the potential effectiveness of the two-stage pipeline, some speed up occurs. To gain further speed up, the pipeline must have more stages. Let us consider the following decomposition of the instruction processing. Fetch instruction, read the next expected instruction into the buffer, decode the instruction, determine the opcode and the operand specifiers, calculate operand, calculate the effective address of each source operand. This may involve displacement, register indirect, or other form of address calculation. Fetch operands, fetch each operand from memory. Operands in registers need to not be fetched. Execute the instruction, perform the indicated operations, and store the result, if any, in the specified destination operand location. And finally, write operand, store the results in memory. With this decomposition, the various stages will be performed nearly equal in duration. So we're just seeing these listed here. You can imagine this is just like a pipeline going from one to the other. So here we're seeing this pipeline in a linear fashion with no issues. And so let's walk through this situation first. For the sake of illustration, let's assume equal duration. Using this assumption, figure 610 that we're showing now shows a 6-stage pipeline can reduce the execution time from 9 instructions from 54 time units to 14 time units, a large savings. Several comments are in order. The diagram assumes that each instruction goes through all 6 stages of the pipeline. This will not always be the case. For example, a load instruction does not lead the WO stage. However, to simplify the pipeline architecture, the time is set up assuming that each instruction requires all 6 stages. Also, the diagram assumes that all of the stages can be performed in parallel. In particular, it is assumed that there are no memory conflicts. For example, the FI, FO, and WO stages involve a memory access. The diagram implies that all of these accesses can occur simultaneously. Most memory systems will not permit that. However, the desired value may be in cache, or the FO or the WO stage may be null. Thus, much of the time memory conflicts will not slow down the pipeline. Several other factors serve to limit the performance enhancements. If the 6 stages are not of equal duration, there may be some waiting involved at various pipeline stages, as discussed before in the 2-stage pipeline. Another difficulty is the conditional branch instruction, which can invalidate several instruction fetches. A similar unpredictable event is an interrupt. So here we're seeing a more or less perfect scenario, which isn't realistic, but let's now go to something that's more realistic and talk about how that would work. So this is where a conditional branch on an instruction pipeline can affect things. Figure 1611 illustrates the effect of the conditional branch using the same program as illustrated in figure 610, which we just showed. We assume that an instruction 3 is a conditional branch to instruction 15. Till the instruction is executed, there is no way of knowing which instruction will come next. The pipeline in this example simply loads the next instruction in sequence, instruction 4, and proceeds. In figure 1610, the branch is not taken, and we get the full performance benefit of the enhancement. In figure 1611, the branch is taken. This is not determined until the end of unit 7. At that point, the pipeline must be cleared of the instructions that are not useful. During time unit 8, instruction 15 enters the pipeline. No instruction completes during the time units 9 through 12. This is a performance penalty because we could not anticipate the branch. So this is the kind of delay that would start to happen that we need to think about. Figure 1612 indicates a logic needed for pipelining to account for branches and interrupts. Other problems arise that did not appear in our simple 2-stage organization. The CO stage may depend on the contents of a register that could be altered by previous instructions that is still in the pipeline. Other such registers and memory conflicts could occur. The system must contain logic to account for these types of conflicts. To clarify pipeline operation, it might be useful to look at an alternative depiction. Figure 1610 and 1611 show the progression of time horizontally, each across the figures, with each line showing the progress of an individual instruction. Figure 1613 shows the same sequence of events with a time progression vertically down the figure, and each row showing the state of the pipeline at a given point in that time. In figure 1613a, which corresponds to figure 1610, the pipeline is full at time 6, with 6 different instructions in various stages of execution, and remains full through time 9. We assume that the instruction 19 is the last instruction to be executed. In figure 1613b, which corresponds to figure 1611, the pipeline is full at time 6 and 7. Time 7, instructions 3 is in the execute stage and executes a branch to instruction 15. At this point, instruction 14 through 17 are flushed from the pipeline, so that at time 8, only 2 instructions are in the pipeline, 13 and 15. From the preceding discussion, it might appear that the greater the number of stages in a pipeline, the faster the execution rate. Some of the IBM 360 designer points out 2 factors that frustrated this seemingly simple pattern for high performance design, and still remain elements that designers must consider. In each stage of the pipeline, there is some overhead involved in moving data from buffer to buffer and performing various preparation and delivery functions. This overhead can be appreciably lengthen the total execution time of a single instruction. This is significant when sequential instructions are logically dependent either through heavy use of branching or through memory access dependencies. Two, the amount of control logic required to handle memory and register dependencies and to optimize the use of the pipeline increases enormously with the number of stages. This can lead to a situation where the logic controlling the gating between stages is more complex than the stages being controlled. Another consideration is latching delay. It takes time for pipeline buffers to operate, and this adds to the instruction cycle time. Instruction pipelining is a powerful technique for enhancing performance, but requires careful design to achieve optimum results with reasonable complexity. Figure 1614a plots the speedup factors as a function of the number of instructions that are executed without a branch. Figure 1614b shows the speedup factor as a function of the number of stages in the instruction pipeline. In this case, the speedup factor approaches the number of instructions that can be fed into the pipeline without branches. Thus, the larger the number of pipeline stages, the greater the potential for speedup. However, as a practical matter, the potential gains of adding pipeline stages are countered by increases in cost, delay between stages, and the fact that branches will be encountered requiring the flushing of the pipeline. The previous subsections, we mentioned some of the situations that can result in less than optimal pipeline performance. In this subsection, we examine the issue in a more systematic way. Chapter 18 revisits the issue in more detail after we have introduced the complexities found in subscalar pipelining organization. Pipeline hazard occurs when the pipeline or some portion of the pipeline must stall because conditions do not permit continued execution. Such a pipeline stall is also referred to as a pipeline bubble. There are three types of hazards: resource, data, and control. A resource hazard occurs when two or more instructions that are already in the pipeline need the same resources. The result is that the instruction may be executed in serial rather than in parallel for a portion of the pipeline. Resource hazard is sometimes referred to as a structural hazard. Let us consider a simple example of a resource hazard. Assume a simplified 5-stage pipeline in which each stage takes 1 clock cycle. Figure 1615a shows the ideal case in which a new instruction enters the pipeline each clock cycle. Now assume that the main memory has a single port and that all instruction fetches and data reads and writes must be performed one at a time. Further, ignore the cache. In this case, an operand reads to or writes from memory cannot be performed in parallel with an instruction fetched. This is illustrated in figure 1615b, which assumes that the source operand for instruction 1 is in memory rather than a register. Therefore, the fetch instruction stage of a pipeline must idle for 1 cycle before beginning the instruction fetch for instruction 3. The figure assumes that all other operands are in registers. Another example of a resource conflict is a situation in which multiple instructions are ready to enter the execution instruction phase, and there is a single ALU. One solution to such resource hazards is to increase available resources, such as having multiple ports into main memory and multiple ALU units. Data hazard occurs when there is a conflict in the access of an operand location. In general terms, we can state the hazard in this form. 2 instructions in a program are to be executed in sequence and both access a particular memory or register operand. If the 2 instructions are executed in strict sequence, no problem occurs. However, if the instructions are executed in a pipeline, then it is possible for the operand value to be updated in such a way as to produce a different result than would occur with strict sequential execution. In other words, a program produces an incorrect result because of the use of pipelining. So there is an example in the text you can follow that shows an x86 machine instruction sequence. I'm not going to talk about that in detail here, just because talking to it without it on the chart won't be very instructive. So keep that in mind. Around figure 16.16, there is some useful details to be following. There are three types of hazards: read after write, raw, or true dependency. An instruction modifies a register or memory location, and a succeeding instruction reads the data in that memory or register location. A hazard occurs if the read takes place before the write operation is complete. There's a write after read or WAR, or anti-dependency. An instruction reads a register or memory location, and a succeeding instruction writes to the location. A hazard occurs if the write operation completes before the read operation takes place. There's a write after write or output dependency. The two instructions both write to the same location. A hazard occurs if the write operation takes place in the reverse order of the intended sequence. The example of figure 1616 is a RAW hazard. The other two hazards are best discussed in the context of superscalar organization, which will be discussed in chapter 18. A control hazard, also known as a branch hazard, occurs when the pipeline makes the wrong decision on a branch prediction and therefore brings instructions into a pipeline that must subsequently be discarded. We discuss approaches to dealing with control hazards next. One of the major problems is designing an instruction pipeline is assuring a steady flow of instruction to the initial stages of the pipeline. The primary impediment, as we have seen, is the conditional branch instructions. Until the instruction is actually executed, it is impossible to determine whether the branch will be taken or not. A variety of approaches have been taken for dealing with conditional branches, having multiple streams, prefetch branch target, loop buffer, branch prediction, and delay branching. Okay, well, let's continue on and talk about multiple streams. So for a simple pipeline, it suffers a penalty for a branch instruction because it must choose one of the two instructions to fetch next, and it may make the wrong choice. A brute force approach is to replicate the initial portion of the pipeline and allow the pipeline to fetch both instructions, making use of two streams. There are two problems with this approach. First, with multiple pipelines, there are contention delays for access to the registers into the memory. And second, additional branch instructions may enter the pipeline on either stream, that is, before the original branch decision is resolved. Each such instruction needs an additional stream. Despite these drawbacks, the strategy can improve performance. Examples of machines with two or more pipeline streams are the IBM 370 and the IBM 3033. So those are a couple examples of things where it's been implemented. When a condition branch is recognized, the target of the branch is prefetched in addition to the instruction following the branch. This target is then saved until the branch instruction is executed. If the branch is taken, then the target has already been prefetched. The IBM 360 uses this approach. A loop buffer is a small, very high-speed memory maintained by the instruction fetch stage of the pipeline and contains the most recent fetched instructions in sequence. If a branch is to be taken, the hardware first checks whether the branch target is within the buffer. If so, the next instruction is fetched from the buffer. The loop buffer has three benefits. One, with the use of prefetching, the loop buffer will contain some instructions sequentially ahead of the current instruction fetch address. Thus, instructions fetched in sequence will be available without the usual memory access time. Two, if a branch occurs to the target just a few locations ahead of the address of the branch instruction, the target will already be in the buffer. This is useful for the rather common occurrence of if-then and if-then-else sequences. Three, the strategy is particularly well suited to deal with loops or iterations, hence the name loop buffer. If the loop buffer is large enough to contain all of the instructions in a loop, then those instructions need to be fetched from memory only once for the first iteration. For subsequent iterations, all the needed instructions are already in the buffer. The loop buffer is similar in principle to a cache dedicated to instructions. The differences are that the loop buffer only retains instructions in sequence and is much smaller in size and hence lower in cost. Figures 1617, which we're showing now, gives an example of a loop buffer. If the buffer contains 256 bytes and byte addressing is used, then the least significant 8 bits are used to index the buffer. The remaining most significant bits are checked to determine if the branch target lies within the environment captured by the buffer. Among the machines using a loop buffer are some of the CDC machines and the Cray1 machine. A specialized form of loop buffer is available for the Motorola 68010 for executing a 3-instruction loop involving the DBCC, that is a decrement and branch on condition instruction. If you want to find out more about that, you can look at problem 1614 for more details. A 3-word buffer is maintained, and the processor executes these instructions repeatedly until the loop condition is satisfied. Various techniques can be used to predict whether a branch will be taken. Among the more common are the following: predict never taken, there's predict always taken, and predict by opcode. So those are some possibility. The predict never taken, these approaches are static. They do not depend on the execution history up to the time of the conditional branch instructions. So all 3 of these ones that we mentioned here. Then we have the taken, not taken switch and the branch history table. These are dynamic and depend on the execution history. So just to repeat again, the first 3 approaches are static. They do not depend on the execution history up to the time of the conditional branch instructions. The latter 2 approaches are dynamic. They depend on the execution history. The first 2 approaches are the simplest. These either always assume the branch will not be taken and can continue to fetch instructions in sequence, or they always assume that the branch will be taken and always fetch from the branch target. The predict never taken approach is the most popular of the branch prediction methods. Studies analyzing program behavior have shown that conditional branching are taken more than 50% of the time. And so if the cost of prefetching from either path is the same, then always prefetching from the branch target address should give better performance than always prefetching from the sequential path. However, in a page machine, prefetching the branch target is more likely to cause a page fault than prefetching the next instructions in sequence. And so this performance penalty should be taken into account as an avoidance mechanism may be employed to reduce this penalty. The final static approach makes the decision based on the opcode of the branch instruction. The processor assumes that the branch will be taken for certain branch opcodes and not for others. There is a reference in the text that reports success rates of greater than 75% with this strategy. The dynamic branch strategies attempt to improve the accuracy of prediction by recording the history of the conditional branch instructions in a program. For example, one or more bits can be associated with each condition branch instruction that reflects the recent history of the instruction. These bits are referred to as taken, not taken switch that directs the processor to make a particular decision the next time the instruction is encountered. Typically, these history bits are not associated with the instructions in main memory. Rather, they are kept in temporary high-speed storage. One possibility is to associate these bits with any conditional branch instruction that is in a cache. When the instruction is replaced in the cache, its history is lost. Another possibility is to maintain a small table for recently executed branch instructions with one or more history bits in each entry. The processor could access the table associatively like a cache, or by using the lower order bits of the branch instruction address. With a single bit, all that can be recorded is whether the last execution of the instruction resulted in a branch or not. Shortcoming of using a single bit appears in the case of a conditional branch instruction that is almost always taken, such as a loop instruction. With only one bit of history, an error in prediction will occur twice for each use of the loop, one on entering the loop and one time on the exiting. If two bits are used, they can be used to record the result of the last two instances of the execution of the associated instruction, or to record a state in some other fashion. Figure 16.18 that we're showing here shows a typical approach. You can also see problem 16.13 for other possibilities. Assume that the algorithm starts at the upper left-hand corner of the flowchart. As long as each succeeding conditional branch instruction that is encountered is taken, the decision process predicts that the next branch will be taken. If a single prediction is wrong, the algorithm continues to predict that the next branch is taken. Only if two successive branches are not taken does the algorithm shift to the right-hand side of the flowchart. Subsequently, the algorithm will predict that branches are not taken until two branches in a row are taken. Thus, the algorithm requires two consecutive wrong predictions to change the prediction decision. The decision process can be represented more compactly by a finite state machine shown in figure 16.19. The finite state machine representation is commonly used in the literature. So if you're not familiar with state machine diagrams, now you got a chance if you just want to take a few minutes to look at this diagram. The use of history bits, as just described, has one drawback. If the decision is made to take the branch, the target instruction cannot be fetched until the target address, which is an operand in the conditional branch instruction, is decoded. Greater efficiency could be achieved if the instruction fetch could be initiated as soon as the branch decision is made. For this purpose, more information must be saved in what is known as a branch target buffer or branch history table. The branch history table is a small cache memory associated with the instruction fetch stage of the pipeline. Each entry in the table consists of three elements: the address of a branch instruction, some number of history bits that record the state of use of that instruction, and information about the target instruction. In most proposals and implementation, this third field contains the address of the target instruction. Another possibility is for the third field to actually contain the target instruction. The trade-off is clear. Storing the target address yields a smaller table, but a greater instruction fetch time compared with storing the target instruction. Figure 1620 Contrast this scheme with a predict never taken strategy. With the former strategy, the instruction fetch stage always fetches the next sequential address. If a branch is taken, some logic in the processor detects this and instructs that the next instruction be fetched from the target address, and that is in addition to flushing the pipeline. The branch history table is treated as a cache. Each prefetch triggers a lookup in the branch history table. If no match is found, the next sequential address is used for the fetch. If a match is found, a prediction is made based on the state of the instruction. Either the next sequential address or the branch target address is fed to the select logic. When the branch instruction is executed, the execute stage signals the branch history table logic with the result. The state of the instruction is updated to reflect a correct or incorrect prediction. If the prediction is incorrect, the select logic is redirected to the correct address for the next fetch. When a conditional branch instruction is encountered that is not in the table, it is added to the table. One of the existing entries is discarded using one of the cache replacement algorithms discussed in Chapter 5. A refinement of the branch history approach is referred to as a two-level or correction-based branch history. This approach is based on the assumption that whereas the loop closing branches, the past history of a particular branch instruction is a good predictor of future behavior. With more complex control flow and structures, the direction of a branch is frequently correlated with the direction of related branches. An example is an if, then, else, or case structure. There are a number of strategies possible. Typically, recent global branch histories, that is, the history of the most recent branches, not just of the branch instruction, is used in addition to the history of the current branch instruction. The general structure is defined as an m, n correlation, which uses the behavior of the last m branches to choose from the 2 to the m n-bit branch predictors for the current branch instruction. In other words, an n-bit history is kept for a given branch for each possible combination of branches taken by the most recent m branches. An instructive example of the instruction pipeline is that of the Intel 8486. The 8486 implementation implements a 5-step pipeline. And so we're showing this pictorially in an example here, and we'll describe it as we're looking at this. First, fetch. The instructions are fetched from the cache or from external memory and placed into one of two 18-byte prefetch buffers. The objective of the fetch stage is to fill the prefetch buffers with new data as soon as the old data have been consumed by the instruction decoder. Because instructions are of variable length from 1 to 11 bytes, not counting prefixes, the status of the prefetcher relative to the other pipeline stages varies from instruction to instruction. On average, about 5 instructions are fetched with each 16-byte load. The fetch stage operates independently of the other stages to keep the prefetch buffers full. Then we have the decoder stage 1. All opcodes of the address and mode information is decoded in the D1 stage. The required information as well as the instruction length information is included in at most the first 3 bytes of the instruction. Hence, 3 bytes are passed to the D1 stage from the prefetch buffer. The D2 decoder can be direct the D2 stage to capture the rest of the instructions, that is a displacement and immediate data, which is not involved in the D1 decoding. Then we have the decoding stage 2. The D2 stage expands each opcode into control signals for the arithmetic logic unit, or ALU. It also controls the computation of the more complex addressing modes. Then we have the execute. This stage includes the arithmetic logic unit operation, cache access, and register update. Finally, we have the write back. This stage, if needed, updates registers and status flags modified during the preceding execute stage. If the current instruction updates memory, the computed value is sent to the cache and to the bus interface write buffers at the same time. With the use of the two decoder stages, the pipeline can sustain a throughput of close to 1 instruction per clock cycle. Complex instructions and conditional branches can slow down this rate. Figure 16.21 shows examples of the operation of the pipeline. So first of all, in figure 1621A, it shows that there is no delay introduced into the pipeline when a memory access is required. However, as figure 1621B shows, there can be delay for values used to compute memory addresses. That is, if a value is loaded from memory into a register and that register is then used as a base register in the next instruction, the processor will stall for 1 cycle. In this example, the processor accesses the cache in the EX stage of the first instruction and stores a value retrieved in the register during the WB stage. However, the next instruction needs this register in the D2 stage. When the D2 stage lines up with the WB stage of the previous instruction, bypass signals allow the D2 stage to have access to the same data being used by the WB stage for writing, saving 1 pipeline stage. Then for figure 1621C, it illustrates the timing of a branch instruction, assuming that the branch is taken. The compare instruction updates condition codes in the WB stage, and bypass pass make the stage available to the EX stage of the jump instruction at the same time. In parallel, the processor runs a speculative fetch cycle to the target of the jump during the EX stage of the jump instruction. If the processor determines a false branch condition, it discards the prefetch and continues execution with the next sequential instruction, which has already been fetched and decoded. So here we have approaches to pipeline organization. In this section, we look at some of the enhancement to a simple pipeline that can be used to improve performance. So we're going to consider a 5-stage pipeline. The instruction fetch loads the instruction from cache, the instruction decode, determines the opcode and the operand specifiers. The operand fetch reads and buffer any register operands. Then we have the execute, which performs the indicated operation for memory load or store. This involves memory access through the cache. Then we have write back, which write backs the instruction results to its destination register. Figure 1622A, it indicates a simple organization for the pipeline. 2 contention problems are apparent. The WB and OF stages both need access to the register, and the IF and EX stages both need access to the cache. Figure 1622B shows modifications to the organizations to alleviate these conflicts. Increasing the number of register ports and buses enable simultaneous read and write. Separating the L1 cache into an I cache and a D cache removes the conflict between the IF and EX stages. Figure 1623 shows a more complex organization that further enhances performance. The following are the changes. Dedicated execution units for each function. Different units can have different time delays, allowing for more flexible pipelining. Pipelining a functional unit because a different functional EX units have different time delays, it is possible to pipeline executions in a longer unit. For example, an integer multiply unit may take multiple clock cycles compared to only one clock cycle for an add subtract and control transfer, instead of having to stall the pipeline until the entire multiply operation is complete. A new EX stage can be started as soon as the first EX stage of the multiply is complete. Then we have the reservation station, a buffer used to hold operations and operands for an EX unit until the operands are available. The purpose of the reservation station is to relieve a bottleneck at the OF stage. The OF can issue an instruction as soon as a functional unit is available and hazards are resolved. The problem this creates is that the OF stage cannot receive a new instruction until the previous instruction has been issued. The reservation stations provide a buffer that enables the OF station to issue instructions as soon as possible. Then the reservation station will dispatch each instruction to its functional unit when the later is available. Figure 1624 shows the typical contents of a reservation station for a machine that will have up to 2 operands per instruction. Each slot shown vertically in the figure hold information for one instruction consisting of one or more tag/value pairs and an OP field. The OP field is the instruction operation command for a functional unit. The tag field indicates valid, quote valid, if the corresponding value field contains an operand. Otherwise, the tag field indicates the identity of the desired operand, such as by using a register number. If the desired operand is available, it is copied from the register to a value field. Otherwise, a slot is a waiting state until the operand is available. The register organization includes the following types of registers. And so here we're looking at table 16.2. These are the x86 processor registers. So for general, there are 8 32-bit general purpose registers. And so you can see figure 16.3c if you want to see that in a figure form rather than table. These may be used for all types of x86 instructions. They can also hold operands for address calculations. In addition, some of these registers also serve special purposes. For example, string instructions use the contents of the ECX, ESI, and EDI registers as operands without having to reference these registers explicitly in the instruction. As a result, a number of instructions can be encoded more compactly. In 64-bit mode, there are 16 64-bit general purpose registers. For segment, the 6 16-bit segment registers contain segment selectors, which index into segment tables, as discussed in Chapter 9. The code segments, that is CS, registers reference the segment containing the instruction being executed. The stack segment, SS, register references the segment containing a user visible stack. The remaining segment registers, DS, ES, FS, and GS, enable the user to reference up to 4 separate data segments at a time. Then we have flags. The 32-bit E flags register contains conditional codes and various mode bits. In 64-bit mode, this register is extended to 64 bits and referred to as R flags. In the current architecture definition, the upper 32 bits of R flags are unused. Then we have the instruction pointers. These contain the address of the current instructions. There are also registers specifically devoted to floating point units. We have also numeric. Each register holds an extended precision 80-bit floating point number. There are 8 registers that function as stack with push and pop operations available in the instruction set. We have control that the 16-bit control register contains bits that control the operation of the floating point unit, including the type of rounding control, single, double, or extended precision, and bits to enable or disable various exception conditions. We have status. So the 16-bit status register contains bits that reflect the current state of the floating point unit, including a 3-bit pointer to the top of the stack, condition code reporting the outcome of the last operation, and exception flags. Then we have tag word. The 16-bit register contains a 2-bit tag for each floating point numeric register, which indicates the nature of the content of the corresponding register. The 4 possible values are 0, special, NaN, or comma, infinity, or non-normalized. That kind of value in the special, what the special is trying to indicate, and empty. These tags enable the program to check the contents of a numeric register without performing complex decoding of the actual data in the register. For example, when a context switch is made, the processor need not save any floating point registers that are empty. The use of the aforementioned registers is easily understood. We can elaborate briefly on several of the registers, which we'll come to shortly. Okay, well, first let's go into more details about the x86 E-flags register. The E-flags register, which we're showing here in figure 1625, indicates the condition of the processor and helps to control its operation, and includes the 6 conditional codes defined in table 13.8, the carry, parity, auxiliary, zero, sign, and overflow, which report the results of the integer operation. In addition, there are bits in the register that may be referred to as control bits. We have the trap flag, where when set causes an interrupt after the execution of each instruction. This is used for debugging. We have the interrupt enable flag. When set, the processor will recognize external interrupts. We have the direction flag. It determines whether string processing instructions increment or decrement the 16-bit half registers SI and DI. That's for 16-bit operation, or the 32-bit registers ESI and DSI for 32-bit operation. The IO privilege flag, when set, it causes the processor to generate an exception on all accesses to IO devices during protected mode operation. We have the resume flag, which allows the programmer to disable debug exceptions so that the instruction can be restarted after a debug exception without immediately causing another debug exception. We have the alignment check. It activates if a word or double word is addressed on a non-word or non-double word boundary. And then we have the identification flag. If this bit can be set in clear, then the processor supports the processor ID instruction. This instruction provides information about the vendor, family, and model. In addition, there are 4 bits that relate to the operating mode. The nested task and T flag indicates that the current task is nested within another task in protected mode operation. The virtual mode VM bit allows the programmer to enable or disable virtual 8086 mode, which determines whether the processor runs as an 8086 machine. The virtual interrupt flag, the VIF, and the virtual interrupt pending, VIP flag, are used in multitasking environment. It might be useful just to pause for a second and just remind ourselves, and this has been a continuing theme as we're going through different parts of computer architectures, there is a lot of complication And as a result, what this does, it gives us a lot of very surgical control in a lot of different areas. And this is also benefiting from decades of research, of exploration, and operational use that trying to be effective. And so here we're thinking from an Intel perspective of trying to be responsive to a wide range of possible ways of how their processors are going to be used by their consumers. Okay, well, let's move on. So here now we're looking at the control registers, and we'll just continue to be thinking through this kind of complexity and surgical control. The x86 employs 4 control registers. Register CR1 is unused as a parenthetical comment. So to control various aspects of the processor operation, we're showing how this works in figure 1626. All the registers except CR0 are either 32 bits or 64 bits long, depending on whether the implementation supports the x86 64-bit architecture. The CR0 register contains system control flags, which control modes or indicate states that apply generally to the processor rather than to the execution of individual tasks. The flags are as follows. First, there's the protection enable, PE, enables or disables protection mode of the operation. There's a monitor coprocessor, MP. It's only of interest when running the programs from earlier machines on the x86 scale of family of what's possible for their processor. It relates to the presence of an arithmetic coprocessor. There's emulation EM. It's set when the processor does not have a floating point unit and causes an interrupt when an attempt is made to execute floating point instructions. There's a task switch, TS. It indicates that the processor has switched task. There's the extension type in ET. It's not used on the Pentium and later machines, used to indicate support of math coprocessor instructions on earlier machines. There's a numeric error in E. It enables the standard mechanisms for reporting floating point errors on external bus lines. We have the write protect. When this bit is clear, read-only user-level pages can be written by a supervisor process. This feature is used for supporting process creation in some operating systems. Alignment mask, AM, it disables alignment checking. Not write through, NW, it selects mode of operation of the data cache. When this bit is set, the data cache is inhibited from cache write-through operations. Cache disable, CD, it disables the internal cache fill mechanism. And we have paging, PG, it disables paging. When paging is enabled, the CR2 and CR3 registers are valid. The CR2 register holds a 32-bit linear addressing of the last page accessed before a page fault interrupt. The leftmost 20 bits of the CR3 hold the 20 most significant bits of the base address of the page directory. The remainder of the address contains zeros. 2 bits of CR3 are used to drive pins that control the operation of an external cache. The page level cache disabled PCD enables or disables the external cache, and the page level write transparent PWT bit control writes through the external cache. CR4 contains additional control bits. So just to think back again, so this previous figure we talked about, it told you the different types of flags, and so you can get some feedback how things are working. And now with this chart, we can be thinking about the control registers, and we're actually putting it into different modes. And we could be thinking of the flags as one way of getting insight as to how well that is performing. So recall from section 13.3 that the x86 MMX capability makes use of the several 64-bit data types. And so this is when we have some complicated multimedia type of things that we're trying to manipulate. So the MMX instructions makes use of the 3-bit register address fields so that 8 MMX registers are supported. In fact, the processor does not include special MMX registers. Rather, the processor uses an alias technique, which we're showing here in figure 1627. The existing floating point registers are used to store MMX values. Specifically, the lower order 64 bits, that is the mantissa of the floating point registers, are used to form the 8-bit MMX registers. And so we have another word here, mantissa, which we haven't used previously, but you think of scientific notation. So the mantissa is what you're going to be multiplying by the 10 times something to the exponent. So the mantissa would be the base number that you have only one digit before the decimal point. Hopefully that helps here. So once again, specifically the lower 64 bits, the mantissa of each floating point register are used to form the 8 MMX registers. Thus, the older 32-bit x86 architecture is easily extended to support the MMX capability. Some key characteristics of the MMX use of these registers are as follows. Recall that the floating point registers are treated as a stack for floating point operations. For MMX operations, the same registers are accessed directly. The first time that an MMX instruction is executed after any floating point operation, the FP tag word is marked valid. This reflects the change from stack operations to direct register operations. The EMMS, empty MMX state instructions, sets bits of the FP tag word to indicate that all registers are empty. It's important that the programmer insert this instruction at the end of an MMX code block so that subsequent floating point operations function properly. When a value is written to an MMX register, bits of the corresponding FP register, that is the sign and exponent bits, are set to all ones. This sets the value of the FP register to NaN, that is not a number, or infinity when viewed as a floating point value. This ensures that an MMX data value will not look like a valid floating point value. So let's talk about interrupt processing. Two classes of events cause an x86 to suspend execution of the current instruction stream and respond to the event: interrupts and exceptions. So we're going to talk about interrupts first here, and then exceptions. In both cases, the processor saves the condition of the current process and transfers to the predefined routine to service the condition. An interrupt is generated by a signal from hardware, and it may occur at random times during the execution of a program. An exception is generated from software, and it is provoked by the execution of an instruction. There are two sources of interrupts and two sources of exceptions. So first, for the interrupts, maskable interrupts is received on the processor's INTR pin. So the processor does not recognize a maskable interrupt unless the interrupt enable flag is set. And then there's the non-maskable interrupts that are received on the processor's NMI pin. The recognition of such interrupts cannot be prevented. Then on the exceptions side, we have the processor detected exceptions, the results when the processor encounters an error while attempting to execute an instruction. And then we have programmed exceptions, and these are instructions that are generate an exception. Interrupt processing on the x86 uses the interrupt vector table. Each type of interrupt is assigned a number, and this number is used to index into the interrupt vector table. This table contains 256 32-bit interrupt vectors, which is the address, that is the segment and offset of the interrupt service routine for that interrupt number. Table 16.3, which we're showing here, shows the assignment of the number in the interrupt vector table. Shaded entries represent interrupts, while non-shaded entries are exceptions. The MMI hardware interrupt is type 2. The INTR hardware interrupts are assigned numbers in the range of 32 to 255. When an INTR interrupt is generated, it must be accompanied on the bus with the interrupt vector number for this interrupt. The remaining vector numbers are used for exceptions. If more than one exception or interrupt is pending, the processor services them in a predictable order. The location of vector numbers within the table does not reflect priority. Instead, priority among the exceptions and interrupt is organized into 5 classes. In descending order of priority, class 1 interrupts on the previous instruction, the vector number 1. Class 2, the external interrupts. This would be 2 and 32 through 255, and so we're referring to items on this list. Class 3, it's faults from the fetching next instruction, so this would be 3 and 14. Class 4 are faults from decoding the next instruction. This would be for items 6 and 7. And then class 5, faults on exceptions, faults on executing an instruction. This would be for 0, 4, 5, 8, 10 through 14, 16, and 17. ARM is primarily a RISC system with the following notable attributes. So ARM is an example of a RISC, and now let's get a little bit more specific. A modern array of uniform registers, more than are found on some systems, but fewer than are found on many RISC systems. And so ARM is a RISC type of processor, but in the range of scheme, it has some, it's not as maybe specialized as some other RISC systems. So that's the first thing, a moderate array of uniform registers. Next, a load/store model of data processing in which operations only perform an operation in registers and not directly in memory. All data must be loaded into register before an operation can be performed. The result can be used for further processing or stored into memory. It also has a uniform length instruction of 32 bits for the standard set and 16 bits for the thumb instruction set. So we talked about the thumb instruction set before, but just think in terms of the 32 bits is the standard way how things are done. But you have a limited instruction set that prioritizes 16 bits within that 32 bits. And sometimes that can be helpful in improving performance for a certain way that you're using the processor. To make each data processing instruction more flexible, either a shift or rotate can pre-process one of those source registers. To efficiently support this feature, there are separate arithmetic logic units, ALU, and shifter units. A small number of addressing modes with the load/store addresses determined from the register instruction fields, indirect or index addressing involved values in memory are not used. Then we have the auto increment and auto decrement addressing modes are used to improve the operation of the program loops. And then finally, we have conditional execution of instructions minimizes the need for conditional branch instructions, thereby improving pipeline efficiency because pipeline flushing is reduced. So continuing on with the ARM architecture and organization, the ARM processor organization varies substantially from one implementation to the next, particularly when based on different versions of the ARM architecture. So the ARM architecture and what it allows has matured, just like the x86 architecture has matured and has tried to have some level of backward compatibility as well as having innovation features in its current release. So once again, the ARM processor organization varies substantially from one implementation to the other, particularly when based on different versions of the ARM architecture. However, it is useful for this discussion in this section to present a simplified generic ARM organization, which is illustrated in figure 1628 that we have in this figure. We're showing here the arrows indicate the flow of data. Each box represents a functional hardware unit or a storage unit. Data are exchanged with the processor from external memory through a data bus. The value transferred is either a data item as a result of a load or store instruction or an instruction fetch. Fetched instructions pass through an instruction decoding before execution under control of a control unit. The latter includes pipeline logic and provides control signals, which are not shown to all the hardware elements of the processor. Data items are placed in the register file consisting of a set of 32-bit registers. Byte or half-word items treated as 2's complement numbers are signed extended to 32 bits. ARM data processing instructions typically have two source registers, RN and RM, and a single result or destination register, RD. The source register values feed into the ALU or a separate multiply unit that makes use of an additional register to accumulate partial results. The ARM processor also includes a hardware unit that can shift or rotate the RM values before it enters the ALU. This shift or rotate occurs within the cycle time of the instruction and increases the power and flexibility of many data processing operations. The results of an operation are fed back to the destination register. Load/store instructions may also use the output of the arithmetic units to generate the memory address for a load or store. The ARM architecture supports several execution modes. Most application programs execute in user mode. While the processor is in user mode, the program being executed is unable to access protected system resources or to change modes, other than by causing an exception to occur. The remaining 6 execution modes are referred to as privilege modes. These modes are used to run system software. There are 2 principal advantages to defining so many different privilege modes. 1, the operating system can tailor the use of system software to a variety of circumstances. And 2, certain registers are dedicated for use for each of the privilege modes, and it allows swifter changes in context. The exception modes have full access to system resources and can change modes freely. 5 of these modes are known as exception modes. These are entered when specific exceptions occur. Each of these modes have some dedicated registers that substitute for some of the user mode registers, and which are used to avoid corrupting user mode state information when the exception occurs. The exception modes are as follows. First, there's superior mode, usually what the operating runs. It is entered when the processor encounters a software interrupt instruction. Software interrupts are a standard way to invoke operating system services on ARM. So we have a abort mode. It enters in response to memory faults. Undefined mode, it's entered when the processor attempts to execute an instruction that is supported neither by the main integer core nor by one of these coprocessors. Then we have the fast interrupt mode. It's entered whenever the processor receives an interrupt signal from the designated fast interrupt source. A fast interrupt cannot be interrupted, but a fast interrupt may interrupt a normal interrupt. We have the interrupt mode. It's entered when the processor receives an interrupt signal from any other interrupt source other than the fast interrupt, and an interrupt may only be interrupted by a fast interrupt. The remaining privilege mode is the system mode. This mode is not entered by any exception and uses the same registers available in user mode. The system mode is used for running certain privileged operating system tasks. System mode tasks may be interrupted by any of the 5 exception categories. So here in figure 1629, it depicts the user visible registers for the ARM. The ARM processor has a total of 37 32-bit registers classified as follows. The 31 registers referred to as the ARM manual as general purpose registers. In fact, some of these, such as the program counter, have special purposes. There are 6 program status registers. Registers are arranged in partially overlapping banks, with the current processor mode determining which bank is available. And anytime 16 numbered registers and 1 or 2 program status registers are visible, for a total of 17 or 18 software visible registers. Figure 16.29 is interpreted as follows. Registers 0 through R0 through R7, registers R15, the program counter, and the current program status registers, CPSR, are visible in and shared by all modes. Registers 8 through R8 through R12 are shared by all modes except fast interrupt, which has its own dedicated registers R8 underscore FIQ through R12 underscore FIQ. All the exception modes have their own version of registers R11 and R16. All exception modes have a dedicated save program status register. Okay, just to use my cursor to help out a little bit here. So for the most part, if you're doing application programming, and if you choose to be doing things in assembly language, this is what you're going to have access to. And we can see how we're going down into privilege mode. The privilege mode would be for the system. We have the supervisor mode and these other modes that we talked about: abort, interrupt, and fast interrupt. And for these exception cases and above, we have some replace type of registers that are used. So you can be keeping that in mind. Okay, so continuing on, the CPSR is accessible in all processor modes. Each exception mode also has a dedicated SPSR that is used to preserve the value of the CPSR when an associated exception occurs. The 16 most significant bits of the CPSR contains user flags visible in user mode, and which can be used to affect the operation of the programs. Figure 1630, as we're showing here, shows these things. And so first of all, we have the condition codes, the N, Z, C, and V flags, which are discussed in chapter 12. And so you might want to go back to that chapter to remind yourself of that. And so let's quickly go into that. So this is the chapter on the digital logic. So let me try and go back and get my place again. So we have the conditional flags. We have the Q flags, which are used to indicate whether overflow and or saturation has occurred in some SIMD oriented instructions. We have the J bit. It indicates the use of special 8-bit instructions known as Jazil instructions, which are beyond the scope of our discussions. And so just keep that in mind. That's a mode that does exist. And you can see that there's a lot of flexibility trying to handle legacy modes and specialized modes. You have the GE bits. This refers to SIMD instructions, use bits, as greater than or equal to flags for individual bytes or half words of the result. The 16 least significant bits of the CPSR contain system control flags that can only be altered when the processor in privileged modes. The fields are as follows: the E bits, control, load, and store, endianness for data. It's ignored for instruction fetches. So we have flags and control bits all in the same one specific register. So keep that in mind. Now we're going through the control bits. Next, we have the interrupt disable bits. The A bit disables imprecise data aborts when set. The I bit disables IRQ interrupts when set, and the F bit disables the FIQ interrupts when set. The T bit indicates whether instructions should be interrupted as normal ARM instructions or thumb instructions. I'll say that again. Indicates whether instructions should be interpreted as normal ARM instructions or thumb instructions. So we have the ability to go from the normal 32-bit word length for an instruction, or we can be using the 16-bit option that cherry picks 16 bits and displays them into that 32 bits. So it's a limited instruction set. Finally, we have mode bits, which indicates the processor mode. So here we're showing table 16.4, the ARM interrupt vector. So we're finishing up on our discussion on ARM here. As with any processor, the ARM includes a facility that enables the processor to interrupt the current executing program to deal with execution conditions. Exceptions are generated by internal and external sources to cause the processor to handle an event. The processor state just before handling the exception is normally preserved so that the original program can be resumed when the exception routine has completed. More than one exception can arise at the same time. The ARM architecture supports 7 types of exceptions. Table so you can, I believe it's table 14.4 lists the types of exceptions in the processor mode that is used to process each type. When an exception occurs, execution is forced from a fixed memory address corresponding to the type of exceptions. Okay, continuing on, I made a mistake earlier. I mentioned table 14.4. It should be the table that we're looking at here. This lists the type of exceptions. So keep that in mind. So these fixed addresses are called the exception vector. So when an exception occurs, execution is forced from a fixed memory address corresponding to the type of an exception. These fixed addresses are called the exception vectors. If more than one interrupt is outstanding, they are handled in priority order. Table 16.4 lists the exceptions in priority order, highest to lowest. When an exception occurs, a processor halts execution after the current instruction. The state of the processor is preserved in the SPSR that corresponds to the type of exception so that the original program can be resumed when the exception routine has completed. The address of the instruction the processor was just about to execute is placed in the link register of the appropriate processor mode. To return after handling the exception, the SPSR is moved into the CPSR and R14 is moved into the PC. Okay, so that's it for the material that we're covering. We got a chance to walk in more depth for the x86 architecture, as well as the architecture for the ARM. And so just review the summary like we had at the beginning. So we talked about processor organization. And so this is where we're thinking. Previously, we talked about the instruction sets. Now we're getting into the more nitty-gritty details of the processor. We talked about the register organization. ones that are available for the users to use and other ones that are not, that are for control and status. We talked about the instruction cycle. There, the fetch executes are the main things, but you can have indirect cycle. We then got into a lot of details on the x86 processor family, the register organization, and the interrupt processing. We got into in-depth discussion about pipelining and what are the strategies, what are the ways that we can be improving performance, including using our best guess of how to prefetch and get things loaded to keep things in a more efficient ways. There are hazards that have to be dealt with. The idea of having multiple branches that you do in parallel. And then we looked at some of the specifics for the 8486 pipelining that they started to introduce with that level of the processor development for the x86 architecture. And lastly, we spoke about the ARM processor as a fixed number of bits used in the each instruction. And we talked about the processor organization, the processor modes, the register organization, and finally the interrupt processing. Okay, a lot of ground there, but this will finish up our lecture for now. Thank you.